Now, here we have to solve some numerical question based on the radioactive disintegration and half-life. So here, example, you can see A is the substrate which is converted into B product, and here initial time was 0, and at the initial time, the initial amount of product was N naught or A. Then this is not actually amount of product, this is the amount of the substrate. So initially we have N naught or A amount of the substrate and reaction is not started. This is the initial situation. And after T time, the new amount created is maybe N, or maybe the initial amount was A. So some part of this A is converted into product now. So that would be A minus X. So sometimes you can use the N and N naught value, or sometimes you can use the A and A minus value. So both are same for you. So it is up to you what you want to use. You can denote it with the N naught and A N. But the key thing here is N naught is the initial substrate amount, N is the final substrate amount. A is the initial substrate amount and A minus X is the final substrate amount. So this you have to remember, and based on these few formulas you have to remember. For example, this particular formula here, K multiplied by T is equals to 2.303 log A divided by A minus X. So A is the initial value here, A minus X is the final value here. So either you just use this 10 or you can use this one as well. A multiplied by T is equals to 2.303 log initial divided by final. K is the reaction constant here. T is the time requirement for the reaction here. How to calculate the half-life? What is the half-life? Half-life is that particular time in which the reaction is half completed, or you can say half the amount of substrate is now converted into product. So both are equal now. That amount of substrate equals to amount of product. So that half time is calculated based on this formula, that is T half 0.693 divided by K. K is the again reaction rate or reaction constant here. How to calculate the average life? Once you have calculated the T half life, just multiplied with the 1.44, that would be the average life of that particular product. So that is how you calculate the average life of the product. Then this is the formula that you have to use when the amount is asked and half life is provided. Full life and half life both are provided in the question. So that is n divided by n naught is equals to 1 divided by 2 in the power t divided by t half. We will see the examples here. Do not panic here. Just you have to remember these formulas. That's all you have to do. So let's see few examples or questions based on these particular formulas. First question is the sodium 24 half-life provided 14.8 hour. What period of time it will lose 90% of the initial concentration? Here are your options: 20 hours, 27 hours, 30 hours, 50 hours. So let's see how to solve this particular question. So here first calculate the reaction rate K, because reaction rate or constant K is not provided. And because half-life is provided, so you can calculate the K easily based on this particular formula. So here the 14.88 is the T half-life is equals to 0.693 divided by K. So K is equals to here 0.693 divided by 14.8. So you will get the K value, which is 4.6 multiplied by 10 to the power minus 2. Now use the final formula. K multiplied by T is equals to 2.303 log initial divided by final. So here T is equals to this K will go to this particular side as a denominator here. So here this particular thing is now 2.303 divided by the K, that is 4.6 multiplied by 10 to the power minus 2, and a log initial amount I am assuming that was 100. And now because in the final time 90% of the material is converted, so the final amount would be 100 minus 90. Only 10 would be left as a final. So 100 divided by 10 or 100 minus 90 you can take. And here this 10 to the power minus 2 will go as a numerator and converted into 100. So this would be 230.3 divided by 4.6 log 100 divided by log 10. So this and this cancelled. Log 10 is equals to 1. So 230 divided by 4.6 is equals to approximately 50 hours. So you can see in the option, the 50 hours is the right answer. So I hope this is clear to you. Very basic calculations. The formula only you have to remember, and easily you can calculate any amount or time requirement for any reaction. So I hope this is clear to you. Then we have another question. If initial concentration of substrate is 32 gram and half-life is provided 1.5 hours, the mass that will remain after 6 hours undecayed would be. This time is provided to you. You have to just calculate the amount that is remain after 6 hours as without conversion into product or as a substrate. So let's see how to solve this particular question. So formula use we will here is n divided by n naught because half life is provided, and 1 by 2 to the power capital T divided by the T half. So capital T full time requirement for the reaction is 6 hours, T half is 1.5 hours. And here the final amount, initial amount was provided, that is 32 gram. So in the place of n naught, I will provide n divided by n naught. In the place of n naught, the initial amount was 32 grams. So n divided by 32 is equals to 1 by 2 to the power 6 divided by 1.5. 6 divided by 1.5 is 4. So this half to the power 4. So what will happen here now? This 32 will come to this side and 2 to the power 4 is 16. So 16, 32 is equals to 2. So the n here, the final amount which would be undecayed or which would be non-reactive or not converted into product, that is equals to 2 gram here, because n is the final amount here. So final amount here is the 2 gram, which is the right answer. So I hope this is clear to you as well. So this formula you have to use in such questions. Next question is saying that 3/4 gram of the radioactive decay in 2 hours. Calculate the half-life of the radioactive material. So now let's see how to solve this one. Again, I will use the same formula because half-life is needed to be calculated here. So n divided by n naught. Let's look into this again. 3/4 gram of radioactive decay in 2 hours. So suppose if I take the n naught is equals to 1. So suppose total 1 of the thing was at the initial amount. The final amount which is left here would be now, because 3/4 is converted. So 1 minus 3 by 4. So this n would be now how much? 4 minus 3 by 4. So this is now n equals to 1 by 4. So in the place of n, only 1/4 amount is left. So the initial amount was 1 and 1/4 of that is left. So in the place of n, I can use 1 by 4, and initial amount was 1. So 1 by 4 divided by 1 is equals to 1 by 4. So that's why in the place of n divided by n naught, I have used 1 by 4 here, because 3/4 amount is left here. So that's why n is equals to 1 by 4 here. That is equals to 1 by 2 to the power 2. 2 is the total time requirement, 2 hours divided by the t half. So 1 by 2 square, I can write down this 1 by 4. So 1 by 2 square is what? 1 by 4. So I can write down like this, and 1 by 2 is equals to 2 divided by t half. So there is a rule in the maths: if a is equals to x and b is equals to y. So I can write down, no, not b. Here this would be also a. So a is a to the power x and a to the power y. So I can write down x is equals to y also, because base are same in the both scenario. So here if x is equals to y, it means 2 is equals to 2 divided by t half. This t half will go this side, and 2 and 2 got cancelled. The answer would be 1 hour here. So here the concept you have to be ready about in this question is, if base are equal in both cases, power will be also equal here. So now this is how this question can be solved. So I hope this is clear to you. Next type of question generally asked from the ion density and the confinement time. So D plus T if the reaction is deuterium plus tritium. So if deuterium and tritium react with each other, then the formula you have to use, that is neta multiplied by tau is equals to 10 to the power 14 second per centimeter cube. So neta here is the ion density. Sometimes in the question ion density is asked, and sometimes in the question tau. Tau means confinement time is asked. So if suppose ion density is asked in the question, so tau value would be provided to you. If tau is asked, ion density value would be provided to you. You have to use that formula only, that is equals to 10 to the power 14 second per centimeter cube. Then deuterium plus deuterium reaction. In that case, Only there would be one change. In the place of 10 to the power 14, 10 to the power 15 you have to use. The remaining things would be unchanged here. And here this is actually per centimeter cube. So if in the question, if it is asking about the per meter cube, then also convert it into per meter cube. Then only you will get your right answer. For example, the question you can see here, for deuterium plus tritium reaction, fusion reaction, the desired confinement time for the ionized fuel is 2 seconds. What must be, this is actually must, what must be the minimum concentration of ions or ion density in ions per meter cube for the net gain of energy? The options are provided here. So you have to use the first formula here, that is D plus T. So in this case, neta multiplied by tau is equals to 10 to the power 14 second per centimeter cube. The tau is provided 2 seconds. So this neta is equals to, the tau will go to the other side. This is 10 to the power 14 second, and this is per centimeter cube. So this 10 to the power 14 divided by 2 now, which is tau. Tau will go to as denominator here. So the neta is equals to here 5 multiplied by 10 to the power 13 ions. Now this second and second would be cancelled. This is second. So these are the number of ions per centimeter cube. But in the question, in the option, you can see the options are in ions per meter cube. So you have to convert this into ions per meter cube. So this would be neta is equals to 5 multiplied by 10 to the power 13. This divided by 10 to the power centimeter cube, you have to convert it into meter cube. So here this would be 10 to the power minus 6, because 10 to the power minus 2 for 1 centimeter, 10 to the power minus 6 or 3 centimeters. So this neta is equals to 5 multiplied by 10 to the power 19. So this is 5 multiplied by 10 to the power 19. C option is the correct option. So this is how you can solve this question. If it is in the per centimeter cube, then the answer you will directly get. If the options are in the meter cube, then just divide it by 10 to the power minus 6. This will go to the upside and this will convert into plus 6. 13 plus 6 is 10 to the power 19. So this is how you can solve the questions of the ion density and confinement time. I hope this is clear to you. Solution is also provided in the PPT so that you can see the same answer you will get here. The few key things that you have to remember in the nuclear reaction, that is best nuclear waste dump site in India, you can find out, or in the world also, the closed mines are the best site. It means where mining is stopped right now, which are also known as the brown field. So brown fields are the best site of the nuclear waste, because every time with the nuclear fission reaction, you will get few amount of wastage there. If the brown field is not available, so we can also dump it out in the volcanic region, or which is also called as the tufts region. The tufts are a very good absorber of the radioactive radiation, so that we can use. Then the temporary storage site, if suppose the time requirement is there for the volcanic region or taking to the brown field, so you can temporarily store it into the water, maybe in the ocean or in the desert site. That is but temporary, because in the desert site or ocean, this can be leaked as well, this can be go out as well, and water and desert would be polluted on that scenario. So the best thing are the closed mines and volcanic region only. And you have to also remember how much energy we are getting from 1 gram of uranium. So just imagine you have 1 gram of uranium that you can taking for the nuclear fusion reaction, fission reaction, and another side you have 13.7 barrels of oil, or maybe 2.4 tons of the coal. So both will give you the equal amount of energy. So you can imagine how big amount of energy you are getting from only 1 gram of the uranium. So that's why the nuclear energy is very, very efficient, very huge amount of energy you will get even with the very small amount of uranium. So that is equals to 13.7 barrel of the crude oil or 2.44 tons of coal. So that is the power of the 1 gram uranium. So this is all about the chapter nuclear energy, and the energy and environment chapter is completed now. So we will start the next unit in the next class. So thank you so much. Meet you in the next class.